Check it out now, y'all.
NanoHub U, online instruction.
Hi, we're back again, and we're here to discuss this experiment that was performed by Compton, and it's referred to as Compton Effect or Compton scattering. And it had, historically, it was a very important result, and I like to explain the experiment and try to explain why it was so important. So first of all, the experiment was performed in 1923 by an American physicist by the name of Compton. He eventually received the Nobel Prize for this experiment. And what he basically did was he took an X-ray tube, right? This produced energetic photons, right? So it's a source of high energy photons. And he directed those X-rays onto a carbon block, which is in this diagram represented by this little square symbol. And he looked at the photons that were scattered by this carbon block. He used a diffractometer, the details of which we don't need to go into. But what he was able to do was he was able to look at the energy of the scattered X-rays as a function of this scattering angle here. And the scattering angle was always defined with respect to the incident beam of X-rays, right? And he measured the energy of the scattered X-rays as a function of the scattering angle theta. So what was expected at the time? Well, what was expected at the time was that if this incident X-ray radiation were represented by photons, there would be a photon incident onto the carbon block, and the energy of each photon would have a value given by Planck's constant h times the frequency f of the X-ray. This energy of the X-ray was basically controlled by the X-ray tube that he used. If that photon interacts with an electron then inside the carbon block, then the electric field of the photon will cause the electron to oscillate up and down. If the electron oscillates up and down, it's going to oscillate at the same frequency as the electric field of the photon. So when the electron emits radiation, it's going to emit radiation at the same frequency. So that means a photon should come out at a different angle, but it should have exactly the same energy as the incident photon, because the incident photon causes an oscillation of the electron at the same frequency as the electric field that the photon has. So there should be no energy loss. That's the bottom line. It's referred to as an elastic scattering process, and that's what experimentally you would expect to observe. You would expect to observe that the X-rays scattered from this carbon block as a function of the scattering angle should have exactly the same energy as the incident X-ray beam. Well, experimentally that was not observed to be true. In fact, what Compton observed was that as the scattering angle was increased, right, a significant number of the scattered electrons lost energy. They came out at longer wavelengths, right? If they come out at longer wavelengths, their frequency is smaller, and if you multiply the frequency times h, you get the energy of the photons. So longer wavelengths corresponds to a loss of energy. And that was completely contradicted by this simple classical argument that was expected to be observed. So what's going on? What Compton did was he analyzed his experimental data by applying energy and momentum principles to explain the data. So he took the results that were well known from collision theory, right, where you've got an object of mass m1 colliding with an object of mass m2. If you know the initial velocities, then you can predict the final velocities and the final directions just based on conservation of momentum and conservation of energy, right? So these were the two conservation principles that he used to explain his data. The only puzzling thing, the only significant difference between these classic billiard ball type collisions and Compton's experiment was that one of these billiard balls was now replaced by a photon, right? And that photon had a particular energy given by h times the frequency f. It was a fair question what the momentum of a photon was, right? You had to come up with an expression for the momentum. Now, why is that puzzling? Well, it's puzzling because classically the momentum is defined as mass times velocity. And what we're trying to do is we're trying to attribute a momentum to a photon, but the photon has no mass, right? It's electromagnetic radiation. So the mass is equal to 0. So, you can't just use this simple expression for momentum of a photon and expect to get anywhere. So what you had to do is you had to come up with a general expression for momentum of a photon. The argument for that is, it's not rigorous, but it gives the basic idea. From Planck, we know that the energy of a photon is equal to h times the frequency f, right? But from Maxwell, we know that, that when an electromagnetic wave interacts with the surface, there's a momentum transfer, and that momentum transfer is equal to the energy u delivered to the surface divided by the speed of light c, right? So if you substitute the energy of a photon in for the expression u that Maxwell would attribute to an electromagnetic wave, then you can find an expression for the momentum of a photon in terms of the frequency or the wavelength lambda of the photon, right? So this is the expression that that Compton would have to use in order to characterize the momentum of the incident photon as it interacts with this block of carbon. So what Compton imagined was an incident photon coming into a carbon block. The incident photon has a wavelength lambda sub I. In the process of penetrating into the carbon block, that electron or that photon interacts with an electron. The electron has a mass m sub e, and the electron is assumed to be at rest, right? You then apply conservation of energy and momentum principles to this collision, and what happens is the electron then recoils, right? So inside the block, the electron acquires a certain energy, and the exiting photon has to lose that amount of energy in order to satisfy conservation of energy considerations. So the energy loss of this scattered photon is attributed to the recoil of the electron inside the carbon block. Now, of course, experimentally, you can't measure the recoil of the electron. That's buried inside the block. But what you can do is you can measure the wavelength of the scattered photon, and then you can infer how much energy is lost to the electron. So Compton pursued this analysis. We're not equipped at this point in time to go through his derivation because he was required to use relativistic mechanics, and we have not yet covered that in this course. So when we discuss relativity towards the end of the semester, we'll be able to come back and derive Compton's formula. At this point in time, we're just going to state it. And the statement of Compton's formula is that the relationship between the final wavelength that's been scattered and the initial wavelength of the X-rays incident onto the carbon block is equal to a constant h over m. M is the mass of the electron, c is the speed of light, times 1 minus cosine theta, where theta is the scattering angle defined with respect to the direction of the incident photon beam, right? So this proportionality constant h over mc has to have units of meters, right? Because lambda f and lambda I are wavelengths. Those have units of meters. So h over mc has to have units of meters, and I just work out evaluate what that proportionality constant is. It's referred to as the Compton wavelength of an electron, and it turns out to be about 2.43 picometers, a very important number in the development of quantum theory. And this will become clear as the semester unfolds. So this is Compton's prediction. I wouldn't be up here talking about it if Compton's analysis did not in fact explain his experimental data very well. So there was some validity to this conservation of energy momentum argument of a photon interacting with an electron that allowed him to explain his experimental data. So we can sort of summarize the experimental results in this diagram. What I show here is I show an electron at rest, I show incident photons striking that electron, and then I show different scattering angles, right? If the X-rays interact with the electron and continue on in a direction that's unperturbed from their initial direction indicated by this black arrow, then the angle theta is equal to 0, and you can see from this equation that the scattered wavelength lambda sub f is going to equal to the incident wavelength lambda sub I, and so there's no energy loss, and this is referred to as an elastic scattering event. If you start to measure the photons scattered at different angles, then the inelastic scattering increases, right? And the inelastic scattering is then measured as the difference between the final wavelength lambda sub f and the initial wavelength lambda sub I. So I just schematically indicate how that separation increases. It reaches a maximum value which is equal to 2 times Compton's wavelength when the photons are actually backscattered from this electron. So qualitatively, this diagram summarizes Compton's experiment, and it shows very nicely how you go from elastic scattering to inelastic scattering. Where the energy lost by the photon increases as the scattering angle increases. So it's a very nice diagram to understand Compton's experiment. As an example, I just worked through some numbers here to give you some feeling for what's actually happening. I like to consider the case where the incident wavelength spans a range of different values, right? So here I've got incident wavelengths of 420 nanometers, which is in the blue region of the electromagnetic spectrum. I go from 420 nanometers all the way down into the X-ray region of the electromagnetic spectrum, where the wavelength is 0.004 nanometers. And in this example, I just consider what happens if the photon is scattered through a scattering angle of 37 degrees. So once I set 37 degrees, then I can evaluate the right-hand side of Compton's formula, right? It's the Compton wavelength, which is this 2.4 picometers times 1 minus the cosine of this scattering angle, 37 degrees. Turns out that's equal to 0.489 picometers. And what that just simply means is that the final wavelength is related to the initial wavelength by this quantity, okay? So the moral of the story is all electromagnetic radiation in principle will Compton scatter from an electron, right? But the shift in wavelengths is going to be so small that when the initial wavelength is up here in the 400 to 40 to 4.2 nanometer range, right? The shift in wavelength is going to be parts per million or tens of parts per million, and it'll be extremely difficult to measure that fractional shift in wavelength. So experimentally, even though the wavelength of the incident light is shifting, experimentally you don't have a chance of actually making a measurement of that energy shift. It's only when you get down into the ultraviolet region, into the X-ray region of the electromagnetic spectrum, that the shift in the wavelength from the initial to the final wavelength is significant. So here it starts to be about 11-12% right, that you can start to make an accurate measurement. So the moral of this discussion is that all electromagnetic radiation should suffer Compton scattering, but experimentally it's very difficult to measure the energy loss when the wavelength of the electromagnetic radiation is large. And so for that reason, you have to confine the measurements experimentally to the X-ray region of the electromagnetic spectrum. Another assumption that you might wonder about is why do we assume that the electromagnetic radiation is scattered just from an electron? Right? This incident electromagnetic radiation penetrates a carbon block. The carbon block contains carbon atoms that could scatter the photons. The carbon block contains protons in the nucleus of the carbon atom that could scatter the photons. There's neutrons inside the carbon block, also confined to the nucleus. They could scatter the incident electromagnetic radiation. Why is it that it's only the electrons that are considered in Compton's analysis? And so what I do to address that issue is I just calculate what the Compton wavelength is for a variety of different objects. So if you assume that the scattering of the incident X-rays is due to the carbon atom, then in this formula you've got to put in the mass of the carbon atom. So the mass of the carbon atom is about 2 times 10 to the minus 26 kilograms. And when you calculate the Compton wavelength for scattering from a carbon atom, you find that the Compton wavelength, this quantity h over mc, is about 10 to the minus 16 meters. Well, that's a number that's extremely small, and again, experimentally would not be measurable. So if in fact the incident photons are scattered from a carbon atom, the exiting photons would have a wavelength shift that would be undetectable simply because it would be shifted by a quantity that's too small to be measured. You can come to the same conclusion for a proton, right? The situation's a little bit better, but you still get numbers on the order of 10 to the minus 15 meters, and wavelength shifts on the order of 10 to the minus 15 meters I don't believe can be measured experimentally. So it's only when you get the mass of an electron, which is really small, right, that you start to measure a significant effect in the energy loss from the incident photon to the scattered photon. So that's something that hopefully is reasonably clear and shouldn't cause confusion in your attempt to try and understand the importance of this Compton scattering. So, is there a physical significance for this Compton wavelength? It's a number that keeps cropping up, and we'll see it later on in the semester when we discuss the energy levels for, let's say, a hydrogen atom. And the physical significance of that Compton wavelength is that if just by manipulating Compton's formula, right, you can show that the Compton wavelength, 1 over the Compton wavelength, is equal to mc squared with a proportionality constant given by Planck's constant times the speed of light. And so what this basically means is, this means that when the rest energy of a particle is equal to, let's say, the frequency or the photon energy, right? When those two things are equal, then you've got a relationship that ties the Compton wavelength to this rest energy, mc squared for the particle. We are not in a position to discuss rest energies at this point. That will come much later in the course, but I wanted to at least make this connection now, because this is Einstein's famous formula, E equals mc squared, and we'll derive that later on, and hopefully you remember that and tie it back to this discussion. The last point I want to discuss is why historically is Compton's experiment so important? And the answer is it was really the experiment that convinced the last skeptics for this photon theory of light. Right? So you recall photons are packets of energy. They had been initially introduced in 1900 by Planck in order to discuss the blackbody emission spectrum from heated objects. The idea that you could treat light as quantized packets of energy was rather remarkable, and there were still skeptics up until 1926 that thought this hypothesis of photons was probably not correct. But when Compton analyzed his data by treating light with a frequency f to have a specific energy and a specific momentum, and when he was able to do the kinematics of that collision between the photon and the electron, it was, you know, the agreement between his theory and experiment that finally convinced the last skeptics that, yeah, light is in fact a particle. It does have a momentum, and its energy is quantized according to the simple formula E equals h times f. So historically, that's why Compton's experiment is so critical, and it sort of sets the stage for the developments of modern quantum physics for the next 75 years or so, right? It finally convinced everybody that light does behave as a particle. So that in itself is a puzzle, and it will form the topic of discussion for the lectures that are going to follow next week. So come back for those, and we'll try to set up the dilemmas that light poses when we try to understand its properties. So I think that's all I got to say for this week. Thank you for listening, and we'll see you later on.